Hello, this presentation is going to be based off of magnetism within medicine, specifically looking into MRIs. All information provided by this video is going to be by group number 7, which is going to be Eric, Savannah, Julia, and myself, and I hope you enjoy this presentation. The history behind the MRI began with the nuclear magnetic renaissance, known as the NMR. The MRIs were based on the theory of nuclear magnetic resonance, which allowed the scientists to study the structure of chemicals developed by Dr. Isidore Rabi. Dr. Raymond theorized that the NMR could be used for medical purposes. In the 1960s, Dr. Raymond theorized that the NMR could be used to identify cancerous cells apart from non-cancerous cells. Part of his theory was that cancerous cells would have more water in them when compared to non-cancerous cells, so the cancerous cells would appear on the MR because of the extra hydrogen atoms found in the extra amount of water cancerous cells have. He tested the theory by using lab rats with cancer and normal lab rats. He published this experiment in 1971. Also in 1971, Dr. Paul developed the first MR image. Like Dr. Raymond, Dr. Paul hypothesized that the MR could be used to identify cancerous cells. He lamented on the fact that he could use dead tissue, so he developed a way to image living tissues with the MR. He was able to develop a way to locate the exact origins of the MR signals and image in 2 or 3 dimensions. The first MR image was 2 water-filled test tubes. Meanwhile, Sir Peter Mansfield developed a way to create a 3D image of the MR. When Mansfield was studying chemical shifts in entropy, he noticed that he added a magnetic field gradient. He could see the structures of the chemicals, which is why he was also able to develop the 3D MR image like Dr. Paul. Each scientist developed a technique to create image using MR. Dr. Raymond used human scanners to create images using MRs, while Dr. Paul used projection reconstruction methods, in which is still used partly today in reconstruction in today's MRIs, while Sir Peter Mansfield's method was known in lining scanning, which involved scanning pieces of structure and when combined created an image. In 1977, Dr. Raymond created the first whole body scanner, and images created were more detailed than X-rays and CAT scans, and Dr. Peter Mansfield developed radio frequencies and gradient coils to create a large-scale image. MRI is short for magnetic resonance imaging or magnetic resonance image. MRIs are used to perform medical examinations. Components that make an MRI is going to be the magnet, which is going to be equaling to about 0.5 to 2.0 Tesla, while the gradient coils produce magnetic fields less strong than the main magnetic field produced by the magnet. Meanwhile, the radio frequency coils, they transmit into radio waves into the patient's body. The patient table allows the patient to slide in and out of the MRI scanner, and the antenna and computer system is where the antenna feeds the computer system the radio signals produced by the patient's body to be able to produce an image. Magnetism plays a very important role in our lives as it is everywhere because it exists in 2 forms. Objects. When magnetism is observed, it is represented by a group of things called dipoles. Dipoles is basically a small unit of magnetization, which consists of a strength and a direction. And in air, when magnetism is observed in air, it is simply called an applied field, where it generally just exists. Because of an object's overall magnetization, it is formed in a way that sends some of its strength into the surrounding air. Also, electricity passing through a wire generates an applied field. We usually observe magnetism in our life without us noticing it in daily life. Some simple examples of magnetism presented in objects of our daily life include home appliances, such as a refrigerator, where the fridge magnet creates a magnetic field that aligns the spins of unpaired electrons in a metal atoms in the fridge in such a way that the magnet and the fridge door are attracted to each other. This force keeps the magnet stuck to the fridge. There are also various other examples, such as computers, microphones, and car horns. In computers, magnets help store data on the hard drive. The way it works is that the magnet inside the device helps change the direction of the magnetic material on the disk in different segments representing computer data. At last, the computer reads the direction of each part of the magnetic material to read the data. Some examples of magnetism presented in a larger scale includes geomagnetic poles. Basically, the Earth is a magnet. However, geomagnetic poles are not the same as north and south poles. The shifting locations of geomagnetic poles are recorded in rocks that form when molten material called magma wells up through the Earth's crust and pours out as lava. When the lava cools and becomes a solid rock, strong magnetic particles within the rock magnetized by the Earth's magnetic field. At last, the particles line up along the lines of the force in the Earth's field. Why is magnetism important? As seen on the previous and large-scale examples, magnetism plays an important role in our daily lives. Furthermore, magnets have been proving its worth every day with its incredible function by making the most strenuous tasks easier. Now that we know the history and components that go into MRI and the use of magnetism and used in daily life, we're going to be looking into a further insight into the physics of an MRI, specifically looking at magnetism. So how does it work? A patient is placed inside a large magnet and must stay completely still for the image to be clear. Contrast agents may be given to the patient intravenously before or during the MRI to increase the speed of the protons. MRI uses the magnetic fields and radio waves to measure how much water is in different tissues of the body, maps the location of the water, and then uses the information to generate a detailed image. The MRI takes scans of sections instead of the whole body because then the result would be unorganized. So what is the MRI used for? MRI scanners are particularly well suited to image the non-bony parts of or soft tissue of the body. These non-bony parts or soft tissues include the brain, spinal cord, and nerves, as well as muscles, ligaments, and tendons. These organs are seen much more clearly with an MRI than with the regular X-rays and CT. The physics behind an MRI. The MRI scanner is essentially a giant magnet. The strength of the magnets is measured in the unit called Tesla. As mentioned before, the MRI uses magnetic fields and radio waves to measure how much water is in different tissues of the body. The MRI machine can only see the hydrogen nuclei contained in the water molecules. The patient, like all of us, has water molecules distributed all over. As you follow the arrows of the pictures, you will see how the MRI views patients. The red dots are hydrogen nuclei inside the patient's body. The MRI machine applies a current to a low-energy hydrogen nuclei, producing the coil. Then it produces the energy in the form of a rapidly changing magnetic field. The frequency of this changing field is called radio frequency energy, also known as RF energy, and the coil is called a radio frequency coil, also known as a RF coil. The hydrogen nuclei with low energy is absorbed. The absorption of the RF energy changes the energy state of low energy hydrogen nuclei. Once the low energy nuclei absorbs the energy, they change their spin direction and become high energy nuclei. Once the RF energy is stopped, the hydrogen nuclei that recently became high energy becomes low energy and starts releasing the energy that was given to them. The MRI machine has receiver coils that receive the energy waves sent out by the nuclei. Having given up their energy, the nuclei change their spin direction and return to the low energy state that they were in before. The receiver coil converts the energy waves into electrical current signals. In this way, the MRI machine can detect hydrogen nuclei within the body. Because radiation is not used, there is no risk of exposure to radiation during MRI procedures. However, due to the use of strong magnets, the MRI cannot be performed on patients with implanted pacemakers, intracranial aneurysm clips, cochlear implants, certain prosthetic devices, implanted drug infusion pumps, neurostimulators, bone growth stimulators, certain intrauterine contraceptive devices, or any other iron-based metal implants. I hope you enjoyed this presentation of magnetism in medicine provided by group number 7. Thank you for watching.